All right, so if two linear equations, right, those are straight lines, in a system have the same graph, the graphs are coincident lines or the same line. There are infinitely many solutions of the system because every point on the line represents a solution of both equations. So what this means is that we have one line. I think I'm going to use highlighters just for this because sometimes it's easier just to. So you have one line, right? I'm just using a highlighter for this line. And then there's another line right on top of it. Okay? And I'm going to use pink for this one. So there's another line right on top of it. And so there's two lines. So when you have two lines which are the same line, right, they are going to have two characteristics. Number one, they're going to have the same slope. And then they're going to have the same y-intercepts. Okay, and remember, this is really, we were talking about some different solutions, and we had one option, which is one solution where you have two linear equations and they cross in one point, right? And that's a consistent. And then the second was a option was you have two linear lines and they never intersect, which was no solution, and that which is an inconsistent system, and they had no solution because they are parallel lines, they have same slope and different y-intercepts. And this is the third where we really have an infinite amount of solutions. And because you have two lines which are the same line, and you just have the same line, right? Two lines that are the same. So this is really the third scenario. And why it has infinite solutions is, it's really, you go back here, right? The solution is where they cross, and so they only cross in one point here. Here they never cross, so there's no points that they have the same, which is the same point is on this graph, which is also in this graph. So that's why it's no solution. But here, since they're the same line, there's like an infinite amount of points which are on both of the lines. That's why there's an infinite amount of ordered pairs, and you could just keep, you know, drawing. There's a ton of options. That's why they say that there's infinite, right? And both of these lines keep going on forever, so that means the amount of solutions that they both have in common just keep going on and on forever as well. So this is really the third option. So we had the first option is one solution, then we had no solution, and now visually we're looking at what infinite solutions looks like. Okay? Perfect. Let's go ahead and look at some problems here. So the first one right here, example 2. So we're going to be looking at systems with infinitely many solutions. So we want to show, we're going to have this problem here. We're going to show that it has infinitely many solutions. And we know when something has infinitely many solutions, we're dealing with the same line, right? So this means we're dealing with the same line, which should have, it's the same line, it should have the same slope and the same y-intercept. So the first thing we're going to do is compare the slopes and the y-intercepts, then graph. So to do that, we need to put it in slope-intercept form. Do you remember what slope-intercept form is? Right? That's y equals mx plus b. Okay. So let's go ahead and do that. This first one is already in slope-intercept form. However, this one's not. So let's go ahead and try that one first. Okay, I'm just going to solve it for y. And I'd say most of the time, like when you have y over here, you usually like get everything away from y, so you move everything else. But this is like one technique that it actually, if you use this technique, it's actually a lot easier. So instead of like moving everything else, moving the 3x, moving the 2, and then it's negative, so we had to multiply it all by -1 to get y positive by itself. Like here, it's actually super easy if I just leave this stuff here where it is and then just move the y, because there's nothing but 0 over here. So once I do the opposite of -y, basically what I've done is now I have y by itself. So if I just use a little bit of symmetric property of equality, now make sure you write that, so it's mx plus b, put the x in front. I have my slope-intercept form. And it's so funny because like I was doing this for years, and probably like in college, and I would always move the 2 and then the 3 and then multiply. And then one time I was looking, I think maybe when I was teaching here. So I've been doing math for so long. And then I saw this and I'm like, oh my gosh, I could have been doing that so long ago and saving myself so much time. And it's just super, like way easier. So there's that technique. There's always little tricks in the book, you know, that just make your life a little easier. Okay, so now we have both of these in slope-intercept form. So I'm just going to look at them. So I'm going to look at this first one here, which we just solved. And then I'm going to look at the second one, which was right here. And, you know, it just looks pretty obvious once you solve them both for y. But we'll go through it, right? You need the slope. This is the slope. And the slope here is m equals 3. And then you need the y-intercept, which is here. And our y-intercept is a positive 2, or just 2. And we're going to look here. Our slope, m is 3. Our y-intercept is, what is our y-intercept? It's 2, b equals 2. So let's see here. Oh, where's my color? Oh, right. I like this. So we have the slope, which is the same. And we have y-intercepts, which are also the same. So since we have the same slope and the same y-intercept, we know that we have the same line, which means we have infinite solutions. So we have the same slope and same y-intercept, So we have the same line. Then I'm going to use therefore. Therefore, we have infinite solutions. That's not how you spell solutions. Solutions. Okay, so that's our answer. This is the reasoning why we get to our answer. This is showing all the work that backs up our reasoning to the answer, but we're also going to graph it as well. So let's go ahead. I'm going to graph the first one, but I'm actually going to graph the blue one just because, so plus 2, that's the y-intercept, and then the slope is 3, 1, 2, 3 over 1, right? I'm going to do one down. 1, 2, 3, 1, 2, 3 over 1, right? 1, 2, 3 over 1. So the reason why I'm doing the blue one first is that blue is a lighter color, and it's always easier for a darker color to go over a light color than for a light color to go over a dark color, if that makes sense. Just for visually it's showing up. So that's our first, and then we're going to do the same thing, right? Our y-intercept for this one is 2, up 3 over 1. It's the same thing. It's the same line. And then this line's probably just going to turn purple. But if I would have ever tried to put the blue over the purple, it would have never shown up. So I'm just going to do that so you can see both. So there we have it. Same line, infinite solutions. infinite amount of solutions along this, right? All of these are solutions that if you stuck in any of those solutions into both of those equations, you would end up with true statements at the end. Okay, so that is the method one of putting both of the equations into slope-intercept form, comparing the slopes, comparing the y-intercepts, showing that they're the same line because they have the same slope and the same y-intercept, which means they have infinite solutions. Then we graphed it. We can clearly see that it's the same line. However, we're going to solve this same problem a different way, and that's through doing it algebraically, okay? So either through substitution or elimination, and I think it's pretty clear that the easiest way would be to do it with substitution because this one's already solved for y. So I'm just going to rewrite these two problems. Okay, and if you see here, this one's solved for y. So we're just going to substitute it in there. And if you see there's a negative in front of that y, so we really have to make sure that we put those parentheses in because that negative has to be distributed to both things. So we have to remember to put those parentheses. And then we just solve, right? So we're going to distribute that negative to both items here. Negative and a positive would be -2. What happens? These cancel, and that's totally okay. And then we end up with -2 plus 2, which is 0, right? And so the variables cancel out. That means we're in the realm of infinite solutions, no solutions. However, here we have a true statement, and so we know that we have infinite solutions. I really like doing it algebraically. It just is so simple. So yeah. There we have it. Okay, let's look at another example. So check it out, example 2. We're going to show that this problem has infinitely many solutions. So we're going to compare the slopes and the y-intercepts first, and then graph. So we really need to put both of these into slope-intercept form first, right? This one is, remember, y equals mx plus b, but this one is not. So let's go ahead and change that really quickly. I'm going to write it here. And this is solved for 0, right? So this is a negative y, and we can move everything, but it's super easy for this one just to add y to both sides. Then y becomes positive, and now y is by itself. So just a super easy way to get y by itself. So there we have that equation right there. So now we're just going to look at both of the equations. So the first one, y equals x minus 3. And then the second equation here, y equals x minus 3. Okay, we just want to figure out what are the slopes, what are the y-intercepts, right? If they have infinitely many solutions, that means they're two lines which are actually the same line, and if they're the same line, that means that they have the same slope and the same y-intercept. So we just need to show that. So here, the slope, we have m equals 1. For the y-intercept, we have b equals -3. Over here, the slope is 1. Remember that whenever there's not a number that you can see there, that means that there's a 1 there. And then the y-intercept is -3 here. So what do we have? We have the same slope. And then we'll use blue. We have the same y-intercept. Okay? So since we have the same slope and same y-intercept, we have the same line. Therefore, we have infinite solutions. Which is our answer. But first, let's go ahead and graph these. So I'm going to graph this one first. Y-intercept is -3, slope is 1, which means up 1 over 1. Right there. Okay, where's my little protractor ruler? That's a nice little straight edge. Okay, there we go there. And then I'm going to graph the other one. So again, -3, up 1 over 1. It's the same thing, same line. I'm going to make this one a little bit longer. So just to show that there's 2 arrows, there's purple arrows and blue arrows. Perfect. So that is showing that it has infinitely many solutions by comparing the slopes and y-intercepts and also graphing. Now let's go ahead and show it through algebraically. And if we're looking here, I'm just going to rewrite these problems. What I see, I think the easiest, what do you see? I mean, the easiest is to use substitution, right? Because this is already solved for y, so we're going to substitute that in there for y. And there's a negative in front of y, so make sure that when you substitute this in, that you put it in parentheses. And then -3 equals 0. All right, now we just need to distribute that negative to both items. We get x, negative times x is -x, negative times a negative is a +3. The x minus x, those cancel each other out. We got 3 minus 3, which is 0. And we end up with a true statement, which means we have infinite solutions. So that is it for example 2. We'll see you back in a little bit for example 3.